Hi everyone and welcome to today's broadcast. This webinar is brought to you by the Energy Storage Technology Advancement Partnership, also known as ESTAP. ESTAP is a project of CICA. Today's topic is Flow Battery Basics. This is part one of a two-part webinar series. Our host today is Todd Olinsky-Paul. Todd is the project director for ESTAP, and he's going to introduce today's guest speakers and talk a little bit about ESTAP. Todd, please go ahead.
Okay, and thank you very much. Welcome everyone to today's webinar. This is, as Samantha said, the first of a two-part webinar series on flow batteries, and hope that you will be able to tune in for both parts 1 and 2. I'm going to start by giving a little bit of background information. So before I begin, I'd like to thank Dr. Imre Gyuk from the U.S. Department of Energy, Office of Electricity Delivery and Energy Reliability, and Dan Borneo of Sandia National Laboratories for supporting our energy storage work. So ESTAP is a project of CICA. CICA is Clean Energy States Alliance. We are a nonprofit organization. We work primarily with state clean energy funds to help them in their efforts, and we also have a number of projects that are funded through contracts, and ESTAP is one of them. This project is funded by a contract with Sandia National Laboratories with DOE money. And this is a brief overview of how that works. The purpose of ESTAP, which is, by the way, the Energy Storage Technology Advancement Partnership, is to create new partnerships between DOE and states to advance energy storage by deploying energy storage demonstration projects. We have two key activities. First, to disseminate information to stakeholders, which is what we're doing right now in this webinar. And two is to facilitate these public-private partnerships for energy storage demonstration projects. We have a number of webinars in our archives that we've done over the past years. You can see a sample of them here. And those are available for viewing on our website at any time. And this map gives you an idea of some of the areas where we are currently working with states to develop energy storage programs and projects. And more information, again, is available on our website. So without further ado, I would like to introduce today's guest speakers. Today we are fortunate to have Dr. Imre Gyuk of US DOE, Dan Borneo and Ferreira from Sandia National Laboratories, Charlie Vartanian from UniEnergy Technologies, UET, and Craig Horne from EnerVault. And we will begin with Dr. Gyuk, who will give us an introduction and some background on flow batteries.
Outlined here, and to provide a buffer for the grid, so to provide security to the grid. Of course, costs are a main barrier, and Imre went over some of the costs of the raw materials, which I won't cover. Okay, so stationary storage has to be compared to the gold standard or the more mature technology of pumped hydro in some respects. Of course, this is the low-cost engine and storage of $80 to $200 per kilowatt hour, but it must be kept in mind that resources such as pumped hydro and caves are site-specific. They're limited in geography and where they can be sited. And they also are constrained to high power ratings in the tens of megawatts to gigawatt range per installation. Pumped hydro has a long discharge duration, so it can do high energy storage and has a very high cycle life. So while that has high cycle life and low cost, we do need to look at other options for other sites. Case is one example, and also traditional lead-acid battery technology is a more mature technology. So this is the standard to look at in comparing to when we want to implement flow batteries. It's mature, it operates in the kilowatt to megawatt range, has an intermediate discharge duration, intermediate cost, as well as cycle life. We also look at lithium-ion batteries. It has similar ranges of power, higher cost, higher cycle life. And then we get into flow batteries. Again, has power ranges in the kilowatt to hundreds of megawatt range. It can have this high energy, which Imre discussed, and I'll review briefly on the following slide. And it also has a competitive cost when we're looking at raw materials. However, as a newer technology, balance of plant costs do need to be considered, and has potential for very high cycle life. Because of the lower cost compared to some other battery technologies, the high cycle life, and the potential for high energy, it's been identified as a very promising technology in grid storage. Again, it fits into the renewable profile, has this long cycle life, deep discharge ability, and the ability to be scalable. If you increase the tank size, you can increase the energy. If you increase the stack size, you can increase the power. So it's something that's versatile, which makes the flow battery's ability to decouple energy and capacity novel and useful for grid applications. This is a general schematic of a flow battery, chemistry agnostic. It uses multiple redox states of species for the charge and discharge purposes. Not to repeat too many times, but as Imre said, the energy depends on the reservoir size, so that can be scaled independently from the electrode or cell size or the engine size, as he pointed out. So you can decouple, as we've said, the energy from power. Flow batteries were developed in the 1960s into the 70s. There's been a lot of identification of different chemistries, the earliest being zinc chloride, followed closely by iron chromium redox flow batteries. And the potential of the battery depends on the chemicals used, as was shown in the plot by Imre. For the iron chromium, it's a 1.2 volt potential in the cell, and so this can be tailored by changing the chemistry, and so we can get up to 1.5 in a vanadium battery, which takes advantage of those multiple redox states of vanadium. The cell configuration is shown here. This is a very crude depiction of cell configuration, more for laboratory scale research and testing. Different companies have more advanced architectures that take advantage of flow dynamics to increase power and decrease the auxiliary needs of pumps. But these are areas of ongoing research both in academia and I'm sure within industry in optimizing flow batteries to reduce cost and make them more viable. While I showed previously pure redox flow batteries, there's another type of flow battery that is commercialized, the hybrid flow battery, in which one of the species is plated onto as a solid. In the case of zinc bromine batteries, this occurs so the power and energy is not completely decoupled because of the need for enough surface area for zinc to be deposited. Hybrid flow batteries like zinc bromide do have an even higher potential, so the potential for higher energy density, with some disadvantages that may occur in the areas of toxicity, dendrite growth, higher self-discharge, and the need to strip the battery periodically. And as with any technology, you have to tailor your needs to the technology that best suits those needs. Within Sandia, as part of the Office of Electricity funding portfolio, we do a lot of work in flow batteries, and this research is aimed at not only improving laboratory scale, but working to assist towards greater deployment on the grid. So research we do is in the area of membranes, including separators and membranes, modeling, development into non-aqueous chemistries, and also we work on the applied side in power systems, control algorithms, systems testing, demonstration projects, and so on. So we have identified this as an area of great potential. As I've stated, we're doing ongoing research, and we're seeing demonstrations of flow batteries, which started in the 1980s and 90s, and have increased to more and more demonstrations and larger scale projects that really do approach those bulk needs that Imre identified that we're focusing on for flow battery technologies. So that's the end of my review, and I'll just acknowledge Dr. Gyuk for his support of this project and the Sandians in charge and who helped with this talk. Thanks.
Okay, thank you very much. I'm going to introduce Craig Horne. Craig Horne is Chief Strategy Officer at EnerVault. He's EnerVault's founding CEO and chairman, and in those capacities raised over $25 million in venture and grant funding while building the launch team, creating the commercial strategy, and establishing initial partnerships. He's been leading and participating in the development of energy technologies for over 20 years, including direct experience with electrochemical systems, lead, acid, and lithium-ion batteries, and fuel cells. Today, he leads EnerVault's business development efforts, including policy, market analysis, and application development.
Thank you. If you could advance to the next slide, please. So at EnerVault, our focus is on long-duration, grid-scale energy storage. Recently, we dedicated our first field system. It's rated at 250 kilowatts on an net AC basis, and it will sustain that power for 4 hours, as Imre described in his section. I'll talk a little bit more about the system in the slides ahead, but we see this as really a stepping stone to where we see the big commercial opportunity, and that's in systems that are tens of megawatts and hundreds of megawatt hour for power and energy capacity, respectively. We are developing an iron chromium-based redox flow battery. The distinction of our technology and products is that they can deliver long-duration storage at constant power. They have an unparalleled combination of the 3 key factors: safety, reliability, and low cost for the applications at this scale. And with the way that we have modular power and aggregated energy within our design, it helps us optimize cost. Can we go to the next slide, please? Just a little bit of background in EnerVault. We have a set of strategic investors that span the globe. 3M here in the United States, Total, the energy giant based in France, as well as Mitsui Global and Tokyo Electron based in Asia, as well as some family and traditional VC investors, institutional investors as well. We're a number of different associations worldwide. We try to remain very active in policy and industry organizations, building up the flow battery and energy storage industry in general. We've been recipients of 3 grant awards, the lion's share from the U.S. Department of Energy under Imre's program, the ARA storage demonstration, and that supported the 250 kilowatt field unit that I'll talk about, and very appreciative of that support. We also had matching funds from the California Energy Commission for that, and support from an earlier first concept package system from NYSERDA. And we have a number of different industrial partners that are helping us move relatively quickly, both where we are today and beyond in scale. Next slide, please. Our application focus is really can be highlighted in two main areas. One we call peak capacity plus, and I think an illustration of this is the recent Long Island Power Authority's gas energy storage and demand response RFP. That was earlier this year, where they were looking for 150 megawatts of power capability, but that could be sustained for 12 hours from an energy storage system. These are large systems, 12 to 50 megawatt in power capacity size, and not only to supply be there for peak capacity and as a local resource, generation resource, but also provide black start value, T&D deferral, and other benefits you get with a longer duration energy storage system. The other aspect is what we call clean resilient systems, where you pair renewable energy with a battery unit. This allows you to augment the amount of PV that goes into a site by as much as a factor of 4, depending on how much fossil generation you want to offset to allow you to have a clean grid. And then with extra storage capacity, you can have a degree of resiliency that's unparalleled. And all this really comes from, as we'll talk about, the fact that with our technology, we can really deliver an extra hour of storage at the lowest marginal cost. And that's a key attribute, because in both of these applications, an extra hour of energy storage really has a lower and lower economic value, and you want to have a CapEx curve that matches that value curve. Next slide, please. So this slide is really just a takeaway. It's the obligatory redox flow battery architecture. The thing to note here is that in our system, this is what NASA at Somerset originally developed in the 70s, where the chromium 2,3 couple is active on the negative side, and the iron 3,2 couple is active on the positive side. Now, one of the things Summer mentioned is you have a contamination issue, and one of the things found by NASA at the end of their development is that by putting iron in the negative and chrome in the positive, you actually eliminate that cross-contamination issue, because then what you result in is a system that has the same elements on both sides of the cell, in the positive and negative. And that's just like the vanadium system, but instead we have iron and chrome, 2 elements, to get to that same identical composition on each side. Now, the lower cost of chromium helps compensate, and we still end up with electrolyte that's a lower cost than other systems. And the other positive aspect, or the other attractive aspect of the iron-chrome chemistry then with this iron in the chrome and chrome in the iron is that at full discharge, or 0% state of charge, you actually have chemically identical electrolytes on each side of the cell. And that means that cell is at 0 volts. There's no electrical potential there, therefore no electrical hazard. And that is a natural operating state of the battery. So you can bring this battery system down to 0 volts, where you have complete electrical safety, and then charge it back up when you would like to. And that really gives you a high degree of safety. So at EnerVault, our intellectual property that we developed over the last several years is, number 1, a novel architecture that delivers sustained power, and number 2, innovations that really help make iron chrome commercial. The next slide, please. And this next slide here shows our patented design, which we call the engineered cascade, is a different hydraulic architecture of a redox flow battery system. And this is really designed to deliver long duration or steady power over long durations of time. We can use a wider state of charge range of the electrolyte, so more utilization on a given volume of electrolyte with this design, and we get higher efficiency. Now, the trade-off with this is the response time for this kind of system is on the order of minutes. It's a bit slower than the hydraulically parallel connection of a traditional flow battery architecture. And but we see for the market of long duration steady power a good fit for the EnerVault engineered cascade. Next slide, please. So the characteristics are shown here in this discharge curve, where the system delivers constant power for as long as electrolyte is fed into the system. So if you have more electrolyte, as you see in the bottom right, extending the hour duration. You just basically would keep delivering the electrolyte to the stack set, the engineered cascade, and you would have that sustained power going for longer and longer periods of time. Up in the upper right is an extraction from a study by the Lawrence Berkeley Laboratory. It's a little bit faded, I think, maybe in the webcam, but the hard copy will show this, where the cost of an iron-chrome redox couple is very, very attractive in comparison to many of the other electrochemical couples up there, up to a factor of 10. And so these two attributes of just being able to extend the discharge duration with very low-cost electrolyte means that the marginal cost of an extra hour of storage capacity is amongst the lowest that can be found, and so our CapEx curve matches the value curve. Next slide, please. In the last 4 years, we've been able to scale the technology by a factor of 10 approximately every 2 years, starting off from small-scale systems up through the pilot to the megawatt-hour system. Next slide, please. And the megawatt-hour field unit, we had a dedication a couple weeks ago. There's a 90-second video available on our website at the URL shown above, and please take a look at that. We weren't able to show that during the webcast here, but it has a lot of information, shows the attributes of the system, and again, the support from the Department of Energy really helped make this happen, and it was greatly appreciated. Imre was out at the event, and it was a great time there. Next slide. So just to bring things to a close, our plans going forward is to have 1 to 2 megawatt systems available for installation at the end of 2015, and then the following year be able to get up another order of magnitude in scale. To do this, we're leveraging expertise in the electrochemical process industry. The next slide, please. We have 2 announced partnerships. We have others in play as well that are helping us get there, folks on the design and fabrication side for things like water treatment plants, which have a great analogy to the architecture and construction of a redox flow battery. And these industry capabilities are very key in getting us to scale quickly. And talking about scale, my final slide here then is, as we go up, the way to think about the redox flow battery is really these 4 building blocks of energy is block A, block B is power, block C would be hydraulic distribution, and then we have in block D controls. What we're doing at EnerVault is we're aggregating our power, or our energy rather, within one system, one hydraulic unit. This helps us lower costs, improves operability, and lowers maintenance. And then we're very modular on power around the 1 megawatt level. This allows us to have a redundancy, tuning the power to the application, and being able to offer higher availability to the end user. And that's it on my side. Thank you.
Okay, thank you very much. We had a couple questions for you. One is, what's the designed life of the iron chromium flow battery system, after which it's no longer economical to keep it operating and it needs to be replaced? And what is the payback period?
Okay. So the design life, it's a modular system. The electrolytes will always are a perpetual asset, so they're always usable throughout the life of a project. The rest of the system would be replaced over intervals, and that really depends in a large part on the use case and the number of operating hours in a year. A typical rough parameter is that the set of stacks will last on the order of 10 to 14 years. The hydraulic subsystem would be 20 to 25 years. The power electronics are on the order of 10 years. And so we have a comprehensive O&M model to look at the cost that we can match to a specific application. And then, of course, that specific application really speaks to what the payback period would be. But that could be anywhere from 3 years to 7 years, depending on the application and the specific parameters around it.
Okay, thank you. And does EnerVault manufacture their own batteries?
We manufacture, we sell turnkey systems on an AC basis with a 480 volt bus. We have partners to help fabricate many of the different components in there, and we fabricate certain specific unique subblocks of the system.
Okay, great. I'm going to go ahead and introduce the final presenter for today. I want to thank Craig Horne. I know you need to leave a little early, so I want to go ahead and thank you now for your excellent presentation. The final presenter for today is Charlie Vartanian. He is the Marketing Director for UniEnergy Technologies, or UET, a manufacturer of advanced vanadium flow battery systems for grid-scale applications. He has over 25 years of power industry experience, and prior to his work at UET, he's worked with DNV Kema, A123 Systems, Southern California Edison, the California Energy Commission, Enron Energy Services, and the U.S. Navy. Of course, currently at UET, focuses on matching client goals and market requirements with UET's novel solutions. So I will now hand it over to Charlie. Go ahead, Charlie.
Thank you, Todd, and thank you to CICA for the invitation to participate today. And I think the prior presentations did a great job of answering what flow batteries are and how they work. I do want to briefly just put us in context. UET, we do make an advanced vanadium flow battery. And the advance is in, next slide please. Let's go ahead to the next slide. That features the advanced part of UniEnergy Technologies vanadium battery. Thanks to over 5 years of investment by the DOE and work at PNNL, UET is using the outcome of that work, and that's an advanced electrolyte that doubles the energy density as well as widens the operating temperature range of a traditional vanadium electrolyte. So the good news is all the positives of the traditional vanadium chemistry are preserved, high cycle life being one of the major ones, and in many ways simplicity of operation, which leads to operational flexibility, but at a much higher energy density as well as a wider operating range, which really delivers a more what I consider a utility-friendly product when you incorporate those attributes into the product. So let's go to the next slide, and I'll focus on the product and how it's used, not so much on the chemistry with the prior presentations covering that well. So what do we make? We take all the attributes of our advanced vanadium flow battery, and what we do have is a product that's based on a modular system that's comprised of 4 20-foot containers with the batteries coupled to one inverter container that has a PCS and a isolation and step-up transformer with a nominal rating of 500 kilowatt, 2 megawatt hour. Aspects that are common to most flow batteries. The electrolyte is water-based. Really helps in terms of fire risk management. The chemistry is robust, 20-year life, and that's the commercial characterization. We do sell these as a 20-year system. And the operational flexibility. I'll pause here. A nice compare and contrast with the EnerVault and other chemistries and UET is we do have some I'll call advanced componentry, Nafion membrane being an example. The use of some of these components actually allow for very wide operational flexibility. So as we'll touch on next, this allows aggressive use of the battery, stacked applications. So as an offset for the incremental, more capital up front, we can do coincident and series stacked applications. And that gets to, well, where are these used and how are these used? Next slide, please. Oh, before we get to how they are used, common to flow batteries is a great scalability. Their attributes lend themselves to tens of megawatts, tens to hundreds of megawatt hour. And this gets at a much deeper and richer set of applications on the grid versus the breakthrough chemistries that initially addressed frequency regulation, some of the shorter-term power applications. But this capability translates getting enough power and energy within a footprint that these do compete. For example, as an alternative to a combustion turbine for peaker use. Also, it lends itself to being combined with PV as a hybrid PV system that's dispatchable. We can firm up and then allow PV to be dispatchable. Next slide, please. An example of this flexibility of the vanadium chemistries in general. Here's an example of a test cycle where we're continuously running a frequency regulation signal, but at the same time imparting a longer duration shifting of energy. So we're both doing peak shifting coincident with frequency regulation. Next slide, please. That this is not new to that is probably, but once again, the flexibility allows addressing this range of applications. Next slide, please. I do want to pause here. So again, stepping back from the UET perspective, I do believe this is common to flow batteries. They apply across both the delivery chain, all the way from behind the meter, customer side, through bulk connected, bulk storage connected at the transmission level. They also cut across the applications that range from, again, on the customer side, simple peak reduction for demand charge reduction, and in those markets where there's a big enough differential, energy arbitrage. You get into the distribution level, you can offset and support overloaded distribution substation or circuits and defer the need to upgrade those. At the same time, you can provide bar service to help smooth out voltage problems. Voltage problems sometimes introduced by reverse flow from distributed generation in PV. At this level, I'm also seeing a lot of renewable integration in the 500 kilowatt to 5 megawatt PV ramp management, curtailment mitigation, and that's the strongest energy arbitrage play, and that's when you have otherwise not delivered renewable generation that you can capture with the battery and then return it later. And again, to do that well, you need some energy, and that's when flow batteries really come to the fore as an option. And then going up the delivery chain, I do see ultimately flow batteries as a form of electrochemical pump storage, but I'll call it pump storage plus. It does the bulk energy, but in addition does the more dynamic, flexible operations. For example, I have noted here NERC compliance, doing transient stability support. As an example of where it goes beyond what you could do with pump storage today. Next slide, please. This is some information put together by Stratagen. But what I want to highlight here is a current value proposition that's economic today and for which flow batteries are competing head-to-head with traditional technologies is if you have a low-capacity peaker, that is a peaker plant being built for 40, 50 hours of operation per year, it's just economically superior to invest in an energy storage system where you can meet those periodic peaks. But in non-peak days, be doing frequency regulation, doing grid support, doing black start support, and again, getting at those stack benefits. Just head-to-head, batteries will beat peakers in many project scenarios. Next slide, please. At this point, I'll just say thank you to the audience for your attention and hand it back to Todd for questions.
Okay, thank you very much. We do have a lot of questions, and we're going to try to get to as many as we can. First of all, what ramp rates and response times can be expected from flow batteries?
This is Charlie speaking for UET, and this shared by a number of flow batteries. At the DC level, we've got 1 to 10 millisecond response. At the system level, inclusive of controls, 100 milliseconds. And that's going from anywhere within the allowable state of charge, which is 0 to 100%.
Okay, very good. And what is the conversion efficiency of flow batteries when you include pumps and other, balance of power and parasitic loads?
I'll chime in for UET, and Summer might have a more general view. For UET, at the DC level, it's 80%. The power conversion itself is another 4%, and the parasitics, the pumps, the house power, is another 6%. I hope I did my math right for a total AC round trip of 70%.
Okay, anybody else want to jump in on any of the other types of flow batteries, chemistry types?
I would say nominally, that's what I've seen in the literature, in the 80s range at the DC level, and then dropping down as low as high 40s, but usually in the 50s to 60s for a full system.
And that's round trip?
Yes.
Okay. And there's a question about toxicity, and I realize this is going to be very different for different types of flow batteries. So would a leak in the system be classified as toxic? Maybe Imre or Summer might want to talk about the differences between different types of flow batteries in this regard.
I suppose the word toxic is not a very scientific word. I don't know anything about how that's viewed by different states or regulatory bodies in terms of their codes and standards. But certainly that's I'll just say a very broad statement that's a concern that's novel to flow batteries that have to be addressed on the level for each technology and where it's being cited.
Well, in general, these flow batteries we're talking about are aqueous solutions. The actual amount of material is relatively little. Most of it is water. Flow battery systems generally have a fairly careful plant setup so that even if there are spills or leaks, they go into a catchment basin so that they do not go out into the environment.
And to add to UET's specific case, to build on the prior comments, in terms of health, the toxicity isn't an issue. Vanadium in solution is not a health hazard. What does need to be managed is the acidic solution. So looking at the MSDS type caution triangle, we're at 3 for acidity, 0 for reactivity, and 0 for fire hazard, actually. But you do have to manage a dilute acid solution, and that usually falls well within just existing industrial practice for containment. And in fact, with our product, part of the reason for the containerization is we leak-proof the interior, so there's actually a first and second level of containment inherent in our containerized project. And if someone wanted that third level, just traditional berms or catchment basins would suffice.
Yeah, and we do not expect a fire from any of the flow battery systems.
Okay, very good. Here's a question about price. The questioner says, most of the quotes for flow batteries we see are upwards of $1,000 per kilowatt hour, including PCS. Nowhere near the 250 shown on one of the slides, and I think that might have been Summer's presentation. Can you address the prices?
Yep, that price did not include basically the balance of plant. That does make it more expensive, and anytime you're dealing with a new technology, the prices are going to be higher than they will down the road when it's more commercialized. So that dealt more with where we could get to. and it points to the fact that the raw materials can be much cheaper than, for example, lithium. But yeah, you have to go to each company and get a price, a current price.
Okay. And to share a single data point, I just wanted to share, the 1,000 per kilowatt hour. I'll just share UET. That's indicative of a total installed cost balance of plant site improvements and equipment. Obviously, the battery itself is south of that. But what's good for most flow batteries, there's good line of sight on as scale comes up. They're just simple procurement efficiencies that drive down the cost. So I do want to qualify that there are no breakthroughs in science needed for the most developed forms of flow batteries. Several of us are on the way to a cost reduction curve based on just simple industrial and commercial practices.
Yeah, I should also like to point out that you have to be careful because to find out whether a quoted price is a price for an entire system or for a single battery.
If anyone has a project they'd like quoted, invite that input.
All right. Well, somebody wants to know whether any of these systems are being used in microgrid applications, which is an interesting question. Are there any? Do you folks know of any microgrids that are using flow batteries at this point?
Short answer is yes. It hasn't been announced, I don't think, but there is a flow battery out in the Pacific Islands in a microgrid. There was a microgrid in Tasmania that featured traditional vanadium that worked very well with the wind diesel battery system that reduced diesel quite a bit. And our company, among others, have at least, I'll speak for ourselves, at least 3 island microgrid proposals active.
Okay. Are they susceptible at all to overheating, or are there other issues that we should be aware of?
Because of very large tank size, they're much less susceptible to overheating than any other battery type. You always have concerns in the power electronics, but in terms of the battery itself, that's an advantage of a flow battery.
Okay, good. Here's a question specifically about UET. Oh, go ahead.
I wanted to share, I think it's common to all flow batteries. If you stop the pumps, the reactions stop. And as Summer said, there's such massive thermal mass, usually in the electrolytes, that overheating is not an issue.
Has UET had Sandia do independent performance testing of their system?
Short answer is that that's in process. Their independent equipment and access to their direct measurement our data is active. But I really can't speak beyond that. So that third-party testing with the support of Sandia is just getting started.
Okay, good. Here's a general question, I think, about flow batteries. Is there degradation in performance over time?
Charlie?
For UET, no. If operated within spec, there is no degradation in power, energy capacity, nor efficiency.
Okay. Anybody want to address that with regard to other flow batteries?
Yeah, in general, the material, the electrolyte, is for a redox battery. Is the lifetime is there are no chemical changes, so the lifetime is as large as you want it to be. Other parts conceivably the membrane might need to be changed out. That's not such a difficult job. And electrodes might wear out, but again, those can be changed out.
Those are good points. I should qualify that there's no degradation. In addition to operating within spec, is also sticking to the planned O&M, the maintenance plan. And by unlimited, that's actually limited by the design life of 20 years, at which there is some componentry that's hitting its end of life.
Okay, thank you. I wanted to mention that one of the audience members for the webinar has commented that Redflow, which is another company producing flow batteries, has demonstrated microgrid applications of their zinc bromide battery coupled with PV and diesel generation for village applications in the outback. I assume that means in Australia. So that's an interesting comment.
I'm aware of those.
Okay. Here's a good one. Where can we find case study reports with technical specifications and economic details? Is this something Sandia provides, case study reports?
Yeah, essentially, particularly for the ARA projects, the stimulus projects, after a certain period of monitoring, there will be detailed studies published of both economical and technical performance.
Okay, good. Somebody wants to know if you could compare the efficiency of flow batteries, and would it be in the same range as compressed air, pump storage, or other bulk storage systems?
I think in general, most of these systems are fairly similar in efficiency. Now, there are certain systems like flywheel systems that reach higher efficiencies. That's because flywheels are magnetically levitated and turning in vacuum. But the 70 to 80 efficiency is fairly universal among all different battery types. I'm talking about range rather than.
Okay.
I would like to share that this is one. Do want to share that one challenge is getting the industry to go to common basis and characterize the reporting key metrics like efficiency. And I do want to point to the DOE Energy Storage System Protocol as a good guidance to the industry, as well as EPRI's Energy Storage Integration Council that is focusing on characterization and reporting of capabilities on a common basis. It gets to the heart of you really got to understand what's being presented when a number like that's given. I'll speak for the vendor community.
Okay. Question again on costs. What sort of cost declines would you expect to see in coming years if these technologies start seeing market adoption? We have a cost curve projection for flow batteries.
Craig had one. I think it's a chicken and the egg. If there was the market demand for a UET gigafactory, we're talking about significant cost declines. Again, no breakthrough in science needed. It's just when you have that kind of purchasing power and logistics efficiencies, but all throughout, I've seen good discussion line of sight declines 70%, 60%, or a 30 to 40% decline from current prices. Again, chicken and egg, it's when that demand is there that warrants the scale up.
Okay, and here's a question about urban locations. Are the flow battery systems suitable for urban locations, for example, Los Angeles, downtown, or New York City?
I see no reason why not.
There's slightly lower, or I don't know, I won't qualify with slightly. It is a lower energy density than other technologies, but as long as the economics are there for, acquiring the square footage. I don't know if that question addressed economics or safety.
And you can stack them on top of each other.
Sure.
One question is, can these devices be recharged by renewable energy sources? So if somebody wants to address that.
Yes, they can, just like any type of secondary battery or energy storage device.
Yeah, in many, or if not most cases, that's exactly what we want. For example, the EnerVault battery sits right in the middle of the almond grove. It gets charged by the photovoltaic array, and then it discharges the battery whenever it's needed. And so in effect, it makes the photovoltaics dispatchable. In the case of some other batteries, the connection is directly to a wind development, and it smooths out the wind and again makes it dispatchable. So while it can be charged from the grid, one of its preferred uses is from renewable energy.
Okay, thank you. So I think at this point, I've sort of stretched this to 15 minutes past when we were going to end, and I think we should let people go. But I do apologize to the remaining folks whose questions we did not get to. Feel free to email those questions to me if you'd like, or follow up, and I will try to field them or get the presenters to field them if they're burning issues that you really need to get answered. And the email for me is here on the screen. Also want to thank all our presenters for an excellent presentation, and I want to mention again that we will be following this up with a Part 2 webinar in the coming weeks, and that will feature a whole new set of folks representing additional flow battery companies and products. So please come back for that presentation. We will be sending out invitations for that fairly soon. Any last words, Maria?
Yeah, I just want to apologize to Dan Borneo. We were having a glitch with being able to hear his audio feed as well. I apologize to the audience members, and thank you for hanging in there through all of our difficulties today. But we're hoping you all will tune in to our next event, and I wish you all a pleasant afternoon. Todd, any last words?
Okay, nope, that's it for me. Thanks very much, everybody.